Rate of change in the temperature of an object is proportional. All right, temperature of an object is proportional to the temperature of the object, difference in the temperature of the object and the temperature of the surrounding medium. So we have multiple representations of temperature here. So we have a temperature of an object, proportional, so that's a K. Difference, I don't need to denote that. Temperature of the object, temperature of the surrounding medium. You can denote it any way you want. You just go with O for object, M for medium. But I know that a lot of folks who have a lot of experience in physics, they tend to use the O for original or initial. So you might use the medium value for that, I don't know. But anyway, what we get from this is a rule, dt sub O. Rate of change is implied per unit of time, all right? Because it's cooling or heating, this applies for heating also, over a period of time, right? Proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So that's Newton's law of cooling, and it applies to, I believe, both of these questions, if not, at least this one. But you can see constant temperature, right? It's placed in a freezer at that temperature. Okay, so that's the surrounding medium. That's your T sub M. Because it's constant, you can plug that right in. Initial temperature is 70 degrees. After 5 minutes, it goes to 50 degrees. How much longer does it take to get 37 degrees? All right, so it's telling us that T sub O is variable, T sub M is constant, time is changing, so that's also variable. So you should have a differential equation that solves to give you a relationship between T sub O and lowercase t, with T sub M being subbed in for immediately. So you just pop in the 20 right away. The only thing I caution you about, not so much for me, but for the AP, just check the units. Temperature, they don't usually play around too much, but time, sometimes it's like, after 5 minutes, how much longer will it take to get to 37 degrees? Round your answer to the nearest half hour. You're like, okay, that's annoying. But still, that's part of it. So just be careful, all right? Anyway. All right, 12-ounce glass bottle of liquid is placed in a freezer that's kept at a constant temperature of 20 degrees Fahrenheit. Initial temperature of the liquid is 70 degrees Fahrenheit. After 5 minutes, the liquid's temperature is 50 degrees. How much longer will it take the liquid to reach 37 degrees? So the only thing that's relevant to the startup of the problem is the fact that it's in a constant temperature of 20 degrees Fahrenheit, because everything after that is a condition related to the solution to the differential equation. So I'm looking at d T sub O dt is equal to unknown constant k times T sub O minus the constant temperature of 20 degrees, all right? The temperature of the surrounding medium in this case is the freezer, right? Or at least the temperature produced by that freezer. So what I have here is a differential equation that contains two variables, lowercase t and T sub O. If you want, and it's entirely up to you, I do this a lot, is I just drop the O, because since I'm replacing the T sub N with a constant, I no longer need to distinguish that with another subscript. So I can just let, for example, T sub O be the temperature T. This allows me to not have to write that subscript of 0 every single time. So dt, a little cleaner version of it. You don't have to do that if you don't want. It's just, you'll notice after a little while, man, I'm writing those subscripts very frequently and it's kind of annoying. All right? So clean it up. 1 over t minus 20 dt is equal to k dt. All right, so just separating our variables. Integrate both sides. Left-hand side integrates to what? T minus 20. Right-hand side? KT plus C. All right, then we can kick it over into exponential form. Okay, so that would be T minus 20 in the absolutes is equal to e to the KT plus C. Once you transform that C into a coefficient, again, you could drop the absolutes, but only in that step. T minus 20 equals C e to the KT. And our general solution to the differential equation would be T equals C e to the KT plus 20. All right. So that would be the temperature of the object. Now, if you want to bring back that subscript at this point, that's fine. But look at all the instances in which I did not have to write that little subscript. You know, that one little step there saved me a little bit of energy. Right. Initial temperature of the liquid is 70 degrees Fahrenheit. So that's telling me that when T is equal to 0, lowercase t is equal to 0, capital T is equal to 70. So I'd be saying that 70 is equal to CE to the K times 0 power plus 20. Zero power is going to make your exponent, well, that is the exponent, that's going to make your expression equal to 1. So 1 times C is C. So we're looking at 70 equals C plus 20. So I now know that the C value is equal to 50. All right, so I can modify my general solution to make it a little bit more particular. It's not completely a particular solution because I still need K. But at least I have the C. So 50 e to the KT plus 20. Now those two coefficients really, they should add to your initial temperature. Just generally how it works. And that's because if you replace T with 0, it really just ends up being the sum of these two values at time T equals 0. Right? But it's a quick way of checking that you didn't make a arithmetic mistake. Right? After 5 minutes, the liquid's temperature is 50 degrees. Right? So that's how I'm going to figure out K. When T is equal to 5, the temperature is 50. So I'd be saying 50 is equal to 50 times e to the K times 5 plus 20. All right, so like I said yesterday, you want to clean it up as much as you can in your head, do the arithmetic that way, rather than showing every individual step. So just kind of play it out in your mind. You're subtracting 20, so 50 becomes what? 30. Divided by 50, 3/5. So e to the 5k is 3/5. We need to solve for k, so natural log of both sides, or put it into log form. Either way, you're going to get 5k is equal to the natural log of 3/5. And then we can conclude that k has to be equal to 5 ln of 3/5. Oh, sorry, 1/5 ln of 3/5. All right, so that goes in for k, which is going to allow us to clean things up. And after we go through this, you'll see a little bit of a relationship that kind of comes into play. It's sort of nice, and it allows you to predict what your differential equation solution would be in particular form. But you don't really get it until you do the work at least a couple of times. So we're multiplying T because it's KT, we're multiplying T by this whole shebang here. So it's e to the T over 5 ln of 3/5. This part cleans up kind of nicely. You get 50. The T over 5 coefficient is going to go up and become the exponent of 3/5, but then E and ln will cancel each other. So you're just going to have 3/5 to the T over 5 power. Right? So you can do that work, but if you go back to this step here, where we were cleaning it up and we solved, you got e to the 5k equals ln of 3/5. Whatever that base is, that's actually going to end up being the base in your differential equation solution. But if you even go a little bit further and get to this, what you're looking at is whatever is contained within the log, that's going to be the base. Whatever the coefficient is, that's going to be the power. So you can kind of use your work along the way to get a sense of what the final answer will be. At a minimum, to just kind of confirm what it'll be, but you know, in advance. But you could actually even use it to do the work, right? But you know, at that point, you might look at it and say, well, I've come this far. You know, what's the point of going? You know, avoiding going a couple extra steps to make sure. You know, but you look at all this, and still not finished because we have to answer the follow-up question. But if you look at all this, yep, this arrow. This is the arrow. From here, following this path, that's your calculus. All right, so from here to there. All right, notation aside, this is all algebra 2. Everything after this is pre-calc. Right, algebra 2 into pre-calc. This one path is your calculus. Right, so the hard stuff, the hard part about this problem has nothing to do with the calculus, because you gave me that very quickly. There wasn't even a moment's hesitation when I said, what's the antiderivative of the left-hand side that came with that, the right-hand side that came with that. Took a second for the plus c, but whatever. This stuff is really where the difficulties lie when people struggle with this, and it has absolutely nothing to do with calculus, which kind of sucks, but that's how it is. How much longer will it take this liquid to decrease to 37 degrees? So, more pre-calc. We know that it's got to get to 37 degrees, so that's the temperature. So subtract, divide, 3/5 to the T over 5 will equal 17/50. Log both sides. So I'll just go meh, and one more meh right there. Okay, one more meh. So T over 5 ln of 3/5 is equal to ln of 17/50. Not really expecting a nice answer here. Divide and multiply. Looks like T will be equal to 5 ln 17/50 divided by ln of 3/5. That's really nice.
I know exactly what time that is.
Such a clean answer. The one thing to keep in mind is that your answer is how many more minutes? All right, because it said after 5 minutes the liquid's temperature is 50 degrees. How much longer will it take the liquid to decrease to 37 degrees Fahrenheit? So that minus 5. It will take 5 ln 17 over 50 over ln 3/5 minus 5 minutes. And it was minutes, right?
Yep.
Longer. Alright. Most likely calculator type question, if the numbers are that bad. But then again, if it's a calculator type question, there's a lot of stuff that you could skip here. So we prepare for the worst and hope for the best. We just get a reasonable value here, something that we can relate to. Yeah, I've been having trouble with it, so I'm just gonna roll the dice here, just hopefully get an answer that you all agree with and move on. Because yesterday I spent like half the day with it plugged in and on, trying to make it work, and it would not. So it was like 5.6 more minutes, something like that. So you can check that on your own.